Hello, in this video I'm going to look at partial fraction decomposition. So here we have a rational expression of which is already in its factored form in the denominator. In the numerator we have a polynomial that represents a quadratic equation where it has three terms. Now, in order to decompose this, we have to rewrite it into what we would call the standard form. So the standard form for this, so let's move this over here just a little bit. Okay, now for this one, well, you have three different factors, right? And accordingly, each of those will get their own unknown factors, which in this case, it would be, so let's call it, why not A? So we have A over x minus 3, and then plus, we can call this b, and kind of go in order, if that's okay. So x minus 2, and then plus c divided by x plus 1. Okay. Now, it says that it's actually equal to that left-hand equation, so that's going to be 4x squared minus 9x, and that's going to be plus 11. And all of this is divided by that same denominator, right? And if it was not factored, then yeah, we would have to go through the process of factoring the denominator, which usually in most examples, it tends to be plus or minus 1, 2, 3. But in any case, any technology could basically factor that, or even kind of just using any factor methods that you remember for rational roots, for example. So if we were to multiply by the LCD on both sides, the interesting thing is that each of these factors would cancel out, essentially. So by doing that, what we're saying is that the LCD, okay, so the LCD is that product of all three factors, x minus 3, x minus 2, and we're saying x plus 1, right? Okay, so if we multiply on both sides, then basically you're going to have that equation is going to change, where you're going to have a times x minus 2 times x plus 1 plus b times, well, in this case it'll be x minus 3, x plus 1, and then plus, well, let's go ahead and, why don't we do this? And then just zoom out just a tiny bit. Okay, that should give us some room. Okay, now we're going to go ahead and write that last one, right? So that last one says that c is going to be multiplied by x minus 3, and that's going to be x minus 2. But all of this has to be equal to that polynomial that we have on the right-hand side, which is 4x squared minus 9x, and then plus 11. Now, for this, what we need to do is to basically just plug in any set of values that would cancel out these factors in any case. So here, what I would say strategic values would be -1, 2, and 3. So note that, for instance, if you plug in 3, you're going to have that for x equals to 3, well, basically you're going to have a times 3 minus 2 times 3 plus 1. But then notice that everything else cancels out because 3 minus 3 is 0, 3 minus 3 is 0. But over here, you're going to have 4 times 3 squared minus 9 times 3, and then that's plus 11. Now, notice this, you have 36, and that's going to be 48, and this is going to be 21, right? Okay, so this, well, let me just double check that. 9, it's off. Okay, it's that's going to be 1, right? So that's 1, that's 4a. Okay, so that's going to be 4a equals to, we said 9/36, so 36 minus 27 plus 11, and yeah, that's going to be equal to, I believe, 20. Okay, so this gives us that a, what is a? A is equal to 5. So we find that a is equal to 5. Okay. Now, to continue this, notice this, that we have that a equals 5. But notice that if we plug in the x equals to 2, what is that solving for? It's solving for b in actuality. So you have that that's actually going to solve for b. So we can do that one, and maybe we can do it over here, where we'll just go ahead and say, well, if x is equal to 2, then I know that that's going to be 0, and that's going to be 0. But notice that over here, it's going to give you negative 3b. So you have negative 3b, and that's due to the fact that that's negative 1, and that's 2 plus 1, which is 3, so negative 3. But then over here, you're going to have that that's going to equal to 4 times 2 squared minus 9 times 2 plus 11. Now, 4 times 4 is 16, plus 11 is 27, minus 18. Well, that's going to give you 9. Now, knowing this, you have that negative 3b. This is equal to, essentially, we have that this is going to be, let's see. Well, yeah, so negative 3b equals to 9. And then here, we're going to go ahead and just solve for b. So b is going to be equal to negative 3. Okay. Okay, so here, it looks that we solved for b in this case as well, right? And all that we need to do from there is to essentially solve for c. Now, notice that c can be found by plugging in negative 1. Okay, so I'm actually going to do a little bit something, I'm actually going to do something different, actually. And by that, I mean that I'm going to look at this. If I multiply a and x minus 2 and x plus 1, the leading term is ax squared. Over here, same thing, ax squared. Over here, cx squared. But over here, that has to equal to, it has to equal to 4, right? So from there, that's telling me that essentially that ax squared, so ax squared plus bx squared plus cx squared, now obviously I need an x squared, right? And that equals to 4. Okay, so that's equal to 4x squared, but that's basically saying that a plus b plus c is 4. So, okay, so a plus b plus c equals to 4. But notice this, you have that 5 minus 3, that's going to be 2 when you substitute. So that implies that c is equal to 2. So we have here that the equation can now be determined from our a is 5, our b is negative 3, and our c is equal to 2. Okay, so that means that essentially we've solved it. And even if you would have plugged in -1, you would have gotten the same thing, because by plugging in -1, that becomes a positive, so that's going to be 24. And then by plugging in -1 over here, you have that this is going to be 12. So positive 12c equals to 24, so that means c equals to 2. And notice that, like, once you put this all together, you have what is known as the partial fraction decomposition of your rational function, of which was in its most simplified form, and it was in the factored form in the denominator. So we have that we can write out the solution as, okay, just a moment. So this equals to, we said 5 over x minus 3 minus 3 over x minus 2, and then plus 2 over x plus 1. Okay, so here is our solution. Now, one thing that is interesting is that could we have solved the same exact equation using a different method? Okay, so the answer to that is actually yes, you can. And to do that, though, notice this, that one of that ways would involve solving what is known as a systems of equations. And, if you look at over here, you're going to have to FOIL this. You're going to have to FOIL this. You're going to have to FOIL this. Okay. Now, doing that, that's going to form a system of equations, of which from there, you can incorporate any method that you would wish to use. But here's the thing. There are so many methods that you can use to solve a systems of equations. However, because of the fact that we know the existence of this equation, that means that this system will always have a solution. What does that mean? That means that you have to use a method of which that you would utilize that the system does exist, or that the system is consistent, i.e. the inverse method. So that means that you could solve this equation using systems of equations via the inverse method. But just so that you have an idea what that looks like, you have to realize that essentially you were solving for what? You were solving for the unknowns A, B, and C respectively. Okay, so the unknowns was A, B, and C respectively, but what we don't know is what that system looked like. Okay, and that's because we didn't go about foiling x minus 2, x plus 1, x minus 3, x plus 1, x minus 3, x minus 2. Then from there, grouping everything and saying it has to equal to 4, it has to equal to -9, and it has to equal to 11. And if you look back in your notes, you'll see that if you plug in a specific value, you have to get a certain value that would appear on that polynomial, for example. And in a way, it's like we already know that, because it's like saying that there's a value that would be within that system that you plugged in, and you have to get, you have to get, like, for example, 4, -9, and 11, for example, okay? But what I'm trying to say is that here we did that actually. We picked the values, which just so happens to have been strategic in the sense that it's going to allow us to solve for A, B, and C respectively. But what if I didn't know that? Then it really wouldn't matter, because if you look back in your notes, you see that you can plug in any set of number of points just as long as there's 3 of them, because you have its degree 2. And then from there, you can solve it easily. So like, for example, if you plug in 0, then you know that that's going to be -2a minus 3b plus 6c equals to 11. And then from there, you could probably even use that a plus b plus c equals to 4, for example. But then from there, you could maybe plug in another point in here, for example, because what we just said was that, okay, let me just verify that, for example, that negative 2a minus 3b. Okay, so negative 2a negative 3b plus 6c, we said has to equal to 11. But we already know that, for instance, that what was the a plus b plus c, we know that it was equal to, we said 10, right? No, actually it's not 10. It's 4. Yeah. I don't know why I said 10. Okay, so we have here that that should be 10. Not 10, sorry. That should be 4. Okay, so this is 4. Now, let's say that hypothetically that you went through that process of just saying that, for instance, that you plugged in one value that you didn't realize was strategic, but then you found that one of the constants was given from that result. So look back a little bit or rewind, and you'll see that I found a to be 5. So what that does is it essentially creates a new system, if that makes sense, because look at this. You have that a equals 5, so a equals 5. Okay, so that equals to 5. Negative 2a minus 3b plus 6c equals to 11. But you also have that a plus b plus c equals to 4. Now notice this, doesn't that give you a system that says 1, negative 2, 1, 0, what is this, negative 3, 1, and then from here, yeah, what are we going to have? We're going to have a 0, and then we have a 6, and then we have a 1. But what would that be? That would be such that it's augmented to 5, 11, and 4. Now, notice that this system, if you were to row reduce it, you would be able to row reduce it, because what you could do is either substitute that x equals 5, and now it's a 2 by 3 system. And if you do that, it's kind of like you now just have a easier process of which that you can solve it from here. So what I would recommend in any case is that you would input this system into anything like a calculator or even Desmos, for example, and then you can try to solve it using row operations. So just to demonstrate, like, what do we mean by that? Well, you could always just, input this as a new matrix, and you have to tell it that you want 4 columns. And of course, you know that one of these is 1, 0, 0, and then 5. And then you have 1, 1, 1, and that's going to be 4. But what is this? This is negative 2, negative 3, 6, and let me see that. 11. Okay, so 11. Okay, now I'm just telling the matrix to row reduce. Okay, so we'll row reduce matrix A, and see that it gave the answer right away. That's amazing. That it told me that A is equal to 5, B is equal to negative 3, and C is equal to 2. Now notice this though, that if we would have went the other route, and by that I mean if we would have inputted the coefficient matrix and the column matrix and then utilized matrix multiplication, it would have worked in either case, because what we have here is that A can be just the coefficient matrix and B could be the column matrix. How do we solve that? Via inverse method. So like, just for example, like just to clarify how, like, if we have that there are 3 rows but 1 column, we're going to input the matrix that we have here, and I'm going to put enter, and let's see, let's call this a new matrix, because I think it's yeah, I wanted to be able to edit that matrix A, but it may not let me at the moment. So maybe, yeah, we can go ahead and define a new matrix and then just call it 3 by 3, 3 by 3, and here that is 1, 0, 0, and then that's going to be so we have to be consistent in terms of like the rows, so that has to be the same, and that's going to be -2, that's going to be -3, and then of course that's going to be 6. Okay. Now look at this. Okay, so notice that if I find the inverse of that matrix, it's giving me some big crazy numbers, right? But look at this. If I take that and I multiply it by B, then it gives me the same answer. So that's the inverse method that was being used, versus we can just use systems. But going back to class, one thing to think about is, did we really need to involve systems for something like partial fraction decomposition? And what's kind of interesting is that in actuality, once we have incorporated things like calculus and even calculus 2, then in actuality, the answer is no, actually. You don't need to use systems of equations in actuality. But the idea of recreating a polynomial and think of it as a reverse type of engineering to get to an identity, then that is the concept actually being applied in actuality. And that's kind of interesting, but you don't really begin to see that until like you start looking at things like numerical analysis or even linear algebra.